Hello and welcome to another episode of Risky Business. Today, we are going to be continuing where we left off. So, let's see. We were looking at this line here, and we learned a whole bunch of stuff. So we learned all this stuff about how the PLIC works, and we also found that so our code references this PLIC base address, and so we found that in the code, and it's this address. And then we were looking at the documentation. Let me close this one. Which one was that? This one right here. So we saw that the mapping of the PLIC, it starts at this address, and that's the address of the PLIC base address in the code. So that matches up. And then the next thing I guess to look at would be the PLIC enable offset. So let's take a look at where that was defined. So I believe that was defined in a PLIC.h. And it's 0x2000. So if you were to look at this address that we have here, and we were to add 2000 to it, we would see that would put you right here, which is target 0 enables, right? And then it looks like it's 0x80 between targets. So I believe you can see here in the comments, it says 0x80 per target. So looking at the space between addresses for the different target enables, you can see that this one was 2000 and this one was 2080. So you can see that matches up with what the code is saying. And so let's see what the code is doing. So we're doing the base address plus the enable offset, which puts you at target 0 enables. And then we're adding the hart ID shifted by PLIC enable shift per target, which is defined to be 7. So apparently that should give us some multiple of 0x80 to find the correct target, where the target depends on the hart ID. So I want to read a little bit about this here. So this is chapter 5 of the E3 Coreplex manual, I believe. Yeah, the E3 Coreplex manual. And let me see. Let's go back to chapter 5 now that we confirm that. And I guess let's read through it a little bit. So we got to the point where we were looking at the memory map, and then we jumped to the actual table and took a look at it. So let's continue reading from here. The PLIC memory map has been designed to only require naturally aligned 32-bit memory accesses. Interrupt sources. Sci5 systems can contain both local interrupt sources wired directly to the hart context and global interrupt sources routed via the PLIC. Interrupt sources can include custom coprocessors and accelerators as well as I/O devices. Interrupt source priorities. Each external interrupt source can be assigned a priority by writing to its 32-bit memory-mapped priority register. The number and value of supported priority levels can vary by implementation, with the simplest implementations having all devices hardwired at priority 1, in which case interrupts with the lowest ID have the highest effective priority. The priority registers are all WARL. Interrupt pending bits. The current status of the interrupt source pending bits in the PLIC core can be read from the pending array, organized as 32 words of 32 bits. The pending bit for interrupt ID n is stored in bit n mod 32 or of word n over 32. Bit 0 of word 0, which represents the non-existent interrupt source 0, is always hardwired to 0. The pending bits are read-only. A pending bit in the PLIC core can be cleared by setting enable bits to only enable the desired interrupt, then performing a claim. A pending bit can be set by instructing the associated gateway to send an interrupt service request. And then we have that table we were looking at. And so I think the thing we care most about here in this chapter is the target interrupt enables, because that's what we're messing with. So let's read that. For each interrupt target, each device's interrupt can be enabled by setting the corresponding bit in the target's enables registers. The enables for a target are accessed as a contiguous array of 32 by 32 bit words, packed the same way as the pending bits. For each target, bit 0 of enable word 0 represents the non-existent interrupt ID 0 and is hardwired to 0. Unused interrupt IDs are always hardwired to 0. The enables array for different targets are packed contiguously in the address space. Only 32-bit word accesses are supported. Implementations can trap on accesses to enable for non-existent targets, but must allow access to the full enables array for an extant target. Treating all non-existent interrupt sources enables as hardwired to 0. Okay, so we are doing this, and then we're saying the amount of memory that we're zeroing out is num sources plus 8 divided by 8. And I believe num sources is something we're passing in. So let's take a look at that. So I want to see the actual demo program. So where is this being called? Here's set up the PLIC, and it says PLIC num interrupts, PLIC num priorities is what we're passing into it. So let's take a look at those constants and see what they are. So I'm guessing that's in the platform file. So PLIC. So PLIC num interrupts is 52, and PLIC num priorities is 7. So we're passing in num sources, and num sources is the number of interrupts, and that's defined to be 52. I believe. Yeah, PLIC num interrupts is 52. So this is doing 52 plus 8 divided by 8. So 8 would be, because of bytes, I believe, mem0 would be taking the number of bytes to clear. So if we have 52 interrupts, it's saying 8 bytes per interrupt, I guess. Plus 1 interrupt. So I'm not sure if I follow. I kind of want to take a look at the mem0 again. So this is taking a pointer of uint8t for the base. It's taking an unsigned int for the size. And it's looping over and clearing out the size number of bytes, which is what you'd expect. So first of all, I guess my first question is that we have PLIC num interrupts set at 52. So where is that defined? Where is it defined that we have 52 interrupts? Or is that like the max? I believe the max would be a big number according to this, right? Because like target 0 down to target 15,871. Or are we talking about sources, in which case there's 1023? Because I think this is defined as num sources, so I believe we're saying there is this many possible interrupt sources. And then we're going to the target enables for the appropriate thread, and then we're clearing it to 0 for all the possible sources. So I want to know where we're getting 52 out of that. That is my current question. So I wonder if that wouldn't be defined, probably not in the E3 Coreplex manual, but more specifically maybe the E300 or the one for the actual chip. So here's, okay, yeah, so here's the interrupts for the specific chip that we have. So table 4.1 lists the PLIC interrupt sources in the FE310G000. The PLIC on this chip has a 3-bit programmable interrupt priority field on each interrupt source. So you can see there are 52 interrupts that this supports. 0 is hardwired to 0, no interrupt. 1 is the watchdog. 2 is the RTC, whatever that is. Then there's UART, 0 and 1. Then there's some Q SPI stuff. Then there's GPIO, so there's 32-bit or 32 GPIO. And then the rest of them are these PWM. So now we know where we're getting 52. That's not pulled out of thin air. That's the sources that this chip supports for interrupts. So that gives us some useful information. Now the other thing is we're saying num sources plus 8 divided by 8 for the amount of memory that we're clearing. So like I say, it's in bytes that we're clearing. And if you take 52 and you divide it by 8, that would give you like that number divided by 8. So I want to know like the width of what we're clearing here. So what I'm wondering about is these targets. So there's 0x80. So what's 0x80 in decimal, first of all? Okay, so that's 128. So there's 128 bytes, I guess, between 128 bytes between each target enables. So if there's 128 bytes, I imagine what we're doing is we're clearing those 128 bytes. Well, I mean, if we do the 52 plus 8 divided by 8, that would give us 7.5. So num sources is 52. And we're doing 52 plus 8 divided by 8. That gives 7.5. So that would round down to 7, wouldn't it? Something that doesn't seem right to me. I don't know. Let's go to the demo again. So yeah, we're passing PLIC num interrupts into PLIC init. PLIC num interrupts is 52, which makes sense. And then we're setting, we're calling that num sources. So num sources has a value of 52. We go in here, and now we're saying 52 plus 8 divided by 8. And that's getting passed into the second argument of volatile mem0. Yeah, I think there's 1 bit per interrupt insofar as I don't know if the 3-bitness matters. But if we do num sources plus 8 divided by 8, we get 7.5. We're passing 7.5 into an unsigned int. It seems like a round up to you insofar as, well, if we pass a 7.5 into an unsigned int, wouldn't it chop off the 0.5 and just call it 7? I don't think that would do a round, would it? I mean, I'm not an expert on C, but I'm pretty sure that doesn't round up. So I feel like that passes a 7 into size. So that would be clearing out 7 bytes of space, if I'm understanding this correctly. So I'm still confused about what's going on here. And let's take another look at the hard ID shifted by PLIC enable shift per target as well. So the PLIC enable shift per target is 7. And it's saying hard ID shifted by 7 places. Okay, so insofar as the saying it would pass 7, I mean like if you passed an account that isn't a multiple of 8, and make sure you clear the byte required for the leftover bits. That makes sense insofar as that might be why they're doing that. But I'm still confused why we're clearing 7 bytes specifically. Because there is 128 between the different enables from what I understand. Because it's 0x80 between them. Or that would be 128 bits, wouldn't it? Not bytes. (128) divided by 8. So if that's 128 bits, that would mean there's 16 bytes per enable in the targets. This stuff here. But we're clearing 7 bytes. And I'm still wondering about this computation of how we're picking the target. So we're saying we take the hard ID and then we shift it left 7. So I'm confused because the hard ID, wouldn't that be just a value? So when we get the hard ID, let's go back to the PLIC driver. Or we're in the PLIC driver. Where was that thing where we saw the read CSR? So like, we're just getting a value from a register and passing it into this unsigned long for the hard ID. And that was defined, I think, in this manual. Or was it defined in this manual? Where was that defined? I think it was in this manual. So I want to know, I want to get a refresher on the hard ID register. So it contains the integer ID of the hardware thread running the code. They might not necessarily be numbered contiguously, but at least one must have an ID of 0. So I guess that doesn't really specify how they number them. Like, to me, it seems like the obvious thing you would do is, like, say the first one's 0, then there's 1, 2, 3, you know, just number them like sequentially. But it seems like that's not what this is doing, maybe, because let me show you what I'm thinking. So the thing is, if we have the first one, let's say, is 1, right? Well, the first one's 0, but we'll say that the next one is 1. And then, so we're going to put some zeros in front of that. And then we're going to put some more zeros. Now we're saying if we're going to shift it over 7 places, it goes here, 2, 3, 4, 5, 6, 7. So it ends up being over here. Now, if you did 2, then it would be 1 place further. If you do 3, then, so like, let's keep going with this a little bit. So this is where it ends up if it's 1. Now, if it's 2, it ends up like this. If it's 3, you get something like that. So I guess so that's what we're doing here. Now, I guess my question is, what are these values in hexadecimal? So like if we do binary so that gives you 8. So like this one, you're getting 0, 8, 0, and then this one, you'd be getting 1, 0, 0. This would be like 180, 0. Am I doing that right? So insofar as you're saying you think all the interrupt enable bits are packed together in the first target, so it just needs to set 7 bytes to 0 to clear them all. So if you're setting 7 bytes, and we're saying that, are we saying that there is 1 bit per? Okay, so you're saying you're going by the text in the Coreplex manual section 6.4 and 6.5, which says the interrupt enables use the same format as in 6.4. So let's take a look at that. So Coreplex manual 6. So we were looking at chapter 5. Let's take a look at chapter 6. Or is this the wrong manual? I must be looking at the wrong manual. Are you sure it was the Coreplex manual that you're looking at? Or are you looking at the one for the chip? I'm not sure what manual you're looking at insofar as U5 would be the Unleashed platform. We're on the Everywhere platform. You need to look up the Sci5 E3 Coreplex manual. So if you go to Sci5's website, you'll see that they have 2 different platforms. There's Freedom Unleashed, which is based on the Sci5's U5 Coreplex, and that's a 64-bit architecture that's more fancy. And the Hi5 1 is using the Sci5's E3 Coreplex. It's part of the Freedom Everywhere platform. Okay, so 5.4 and 5.5. So interrupt pending bits. The current status of the interrupts are pending bits. So they're organized as 32 words of 32 bits. Okay, so I mean 32 bits is 4 bytes. So you're saying there's an array of 32 times 4 bytes? Which is 128. Okay, so that's what we calculated earlier. The 128. And then chapter 5.5. So interrupt enables. For each interrupt target, each device's interrupt can be enabled by setting the corresponding bit. So they're 32 by 32 bit words. Packed the same way as the pending bits. Okay, so the 128 would be if you're supporting the maximum number, but we're only supporting 52 interrupts, right? We have 52 different interrupts. So if you only have 52 interrupts, would that be seven bytes? Is that what you're saying? But isn't it 1 bit per interrupt source? If you had 1 bit per interrupt source, that's 52 bits. And 52 bits would be 7 bytes. I get you now. Okay, so it's 52 interrupts. There's 1 bit per interrupt, and because it's 52 bits, that's 7 bytes. And so by clearing those 7 bytes, we're covering all the possible interrupt sources. So I understand now insofar as that makes sense. So that explains why we're doing this this amount of clearing, and we understand this much. Now, the last thing I want to understand about this code, before I feel like we fully understand everything that this line is doing, the last thing I want to understand is this calculation to find the appropriate offset for the target. So like the target should be 0x80 apart, right? Now, when I did my math here, I think you can convert binary to hex by just doing a nibble at a time. So correct me if I'm wrong about that. But if you do a nibble at a time, then 0001, that's just 1. And then 0 and 0, that's 0. And 1000 is 8. So it goes 0, 80, 100, 180. So then is that a step 80? Is that stepping 0x80 at a time is my question. So like 80 to 100, that's not a difference of 20 because it's not decimal, it's hexadecimal. So is it actually a difference of 80? And I'm not good enough with hex to know in my head, is that a difference of 80? Can Google do like math in hex? Like if I say 0x 100 minus 0x 80. Oh, cool, it can. So yeah, it is moving 0x80 at a time. So at this point, I think we finally understand everything that this line is doing. It gets the base address, it adds the enable offset, which finds the target enable, and then the hard ID shifted over 7 places moves it 80 per target. So if it's 0, it lands you on target 0. If it's 1, it lands you on target 1, etc. And then we clear out 7 bytes. And we're clearing 7 bytes because that covers the 52 bits that correspond to every interrupt source that this chip supports. So I think at this point we have fully deciphered this line of code and understand anything and everything about it. So let's move on. I don't know if we need to take any notes about that to cement it in our brain. Let's take a note that hard ID shifted by PLIC enable shift per target gives you steps of 0x80. So hart ID shifted by the PLIC, what do they call it? Like enable shift or something? Enable shift per target. So PLIC enable shift per gives you steps of 0x80, which is the number or the distance between the different target enables. And we're also going to take so hearts, we still don't know for sure what it stands for. We're presuming it stands for hardware thread. I don't know why you'd compact that into HART though. But that seems to be what it is referring to. Oh, there's a terminology section. So it looks like we're correct that it stands for hardware thread. Thank you for pointing that out insofar as which manual was that in that it has a terminology section? Is that this, the privileged spec? So I imagine that would be at the end of it. I'm not seeing a terminology section here. Which PDF are you referring to that has a terminology section? That would be useful. Okay, the E3 Coreplex one has a terminology section. Okay, yeah, so hardware thread is the hart. And then let's read these other terminologies while we're here, because I've been seeing like the WARL and stuff like that thrown around in the documentation. And I don't actually know what that stands for. So the seal int is the Coreplex local interrupts, which includes software interrupts, local timer interrupts, and other interrupts routed directly to a car. Hart is hardware thread. JTAG is joint test action group. PLIC, we already know that one. Tile link, a free and open interconnect standard originally developed at UC Berkeley. WAR, so write any read legal field. WARL is a registry field that can be written with any value but returns only supported values when read. Okay, so we understood that, we just didn't know the term. So that's useful to know. WIRI, writes ignored, reads ignored field. So a read-only register field that may contain unknown information. Writes to the field are ignored, and read should ignore the value returned. Why would you read something if you're supposed to ignore the value returned? That doesn't make any sense to me. And then there is write legal, read legal field. A register field that should only be written with legal values and that only returns legal value if last written with a legal value. And then there's WPRI, writes preserve, reads ignore field. So a register field that may contain unknown information, read should ignore the value returned, but writes to the whole register should preserve the original value. Okay. And it looks like that's all the terminology. So that's good to know. Now they just need a pronunciation guide. Do you mean in terms of the physical size of the Hi5 one, or in terms of the size of the spec of the chip and the board and everything? The spec is small because this is a RISC architecture, and the size of the board is small because it's Arduino compatible, and that's the size of an Arduino apparently. So the last thing I want to take a note of, do we have in our notes that hart is hardware thread? Because I feel like we knew that. I mean, we did know that, but I don't know if we wrote it specifically. because we didn't actually see anything saying that's what it actually means. So we wrote that mHartID is the machine CSR that specifies the ID of the running thread. Let's add a note here that hart stands for hardware thread. And then I also want to add a note about the computation of the size. So we're going to add a note that says the chip that the high-five one uses. I'm just going to say that because I don't want to write out the model number of the chip. The chip that the high-five one uses has 52 interrupt sources. With 1 bit per interrupt source. You can clear them all in the target enables by clearing 7 bytes. Which is what num sources plus 8 divided by 8 is doing. The plus 8 is for rounding. So I think that covers everything that we want to take a note of. And from there, I guess it's time for us to move on to the next line. So the next thing we're doing is we're setting all priorities to 0. And this should be pretty straightforward now that we understand the one for disabling the interrupts. So we're doing a volatile mem0 just like we did before. We're computing the address by doing this PLIC base address, and then we're adding the PLIC priority offset instead of the enable offset. So if we go back to our memory diagram, let's see where that was. Was this the memory map I'm thinking of? It looks like it is. So it looks like the priorities start. Well, there's source priorities and there's target priority thresholds and claim completes. So if we're doing the priorities, we're doing these ones here. So the offset is probably just 4. That would be my guess. Now let's confirm that by reading the source. So that would probably be defined either in the PLIC.h or the platform.h. So priority offset. It's starting at 0. So they start it at the reserved one, which would be, I guess, for a source 0, if you will, rather than starting it at the source 1 priority. So the base address plus the priority offset, where the priority offset is just 0. So that's starting you at the base address. And then there's zeroing out from num sources plus 1, shifted by PLIC priority shift per source. PLIC priority shift per source is 2. So presumably, num sources plus 1 shifted by PLIC priority shift per source should give you the from here to the 52 sources, it's plus 1 because we're starting on the reserved memory instead of on source 1. So it's actually doing 53. And then the shift per source would be the width of it's 4 bits per source. And we could do the math to confirm that, but I think we are just going to use our knowledge of the past one, that this gave the correct, math, to assume that this is giving the correct math as well. I think that's a reasonable assumption to make here. So if we make that assumption, I think we understand everything about this line, and we can move on to the next line. So setting the threshold to 0. It looks like this one is a little bit different. It's actually getting a value out of here and then setting it like this. So the type is PLIC threshold. So where is the PLIC threshold type defined, first of all? So let's check. I'm going to check encoding before I check platform. PLIC. So let's check platform now. It's not defined there either. It's probably in the Sci5 devices PLIC. Or wait, we looked at that already, didn't we? So it's not in any of those files, so we need to do a little bit of hunting again. PLIC threshold. Let's look at PLIC driver.h. So this has the PLIC instance type. Oh, okay. So it's a type def. It's just a uint32. So we've got a uint32 here, and we're getting it from this address. So we're doing the base address plus the threshold offset plus the hard ID shifted by PLIC threshold shift per target. And again, I don't think we need to look at the definitions of those because we understand what they're doing. You can see that it's going to put you right here for the target 0 threshold. It's going to put you right here for the target 1 threshold, etc. So I'm pretty sure I understand what that's doing. And then we're saying we're just going to clear 4 bytes because it's a uint32. So if you're clearing 4 bytes to 0, so it seems like that would be clearing more than we want, wouldn't it? So I'm a little bit confused there. So let's just double check and confirm that it's doing what we're thinking. So the threshold offset is 2000000. And we can see that is indeed the place we're thinking it's going to. And then the shift per target is 12. But the thing I'm confused about, well, first of all, if it's a shift of 12, hard ID shifted by 12. So we looked at the one that was 7, and that's 0x80 per target. But now you're saying this has a threshold shift of 12, which would be even more than 0x80. But if you look at the document here, oh wait, so target 0 and then the target claim complete, I was looking at it and I was saying, well, that's only like 4 bits. But see, the target 1 is way over here at 1000. So that does make sense. I thought it was going by steps of 4, and I was like, whoa, that's like you're jumping way more than that. But no, it's 1000 in hex. So I think that makes sense what this line is doing too. Like the 4 bytes probably corresponds to the width of that. So I think at this point we understand everything that the PLIC init is doing. So I feel happy about that. And I am ready to move on to reading some of these other things. So like here's a PLIC set threshold, and I'm guessing this is going to be really simple. So this gets the thread ID, and then it gets a pointer to the threshold, and that's doing the same computation that we just saw, and then it's just setting the value. So that all makes sense. And then enable interrupt. So again, we get the thread ID. We get a pointer to a uint8t. So this we're going to need to study to see what it's doing here. We get the value, a copy of it, out of the pointer. We do some math on it, and then we set it in the back into the actual location in memory. And this is doing an enable interrupt. So I think we're going to need to take a closer look at that. But we are out of time for today. So thank you everyone who tuned in today. And thank you everyone who watches on the YouTube archive at risky.tv. You can follow me at HMN_risky on Twitter to get updates about this series. And I will see you next time. Stay risky, everyone.